Hello students, welcome back to another video. In today's video, we'll be doing again a paper 4 of 0625 October-November 2024 variant 3. And the first question is saying state the difference between scalar quantities and vector quantities. So what is the basic difference between both of these? Scalar quantities have magnitude only, but vector quantities have magnitude and direction as well. For example, we have two things, speed and velocity. So for speed, we are only concerned with the value or the magnitude. Either it's 3 meter per second or it's 4 meter per second. We are just only concerned with the magnitude. But for velocity, we need the magnitude as well as the direction of speed. Next is define momentum. So momentum is the product of mass of a body times its velocity. Next question is saying a test car crashes into a barrier to test safety features. The car has total mass of 950 kg and it is moving with constant velocity for time t equals to 0 to time 4 seconds, and the car then hits the barrier. Figure 1.1 shows the car as it hits the barrier. So there is a car which is coming to this barrier and they are going to have a collision between them. During the test crash, the resultant force acting on the car is 27,000 newtons and car takes 1.5 seconds to come at rest. The deceleration is uniform. Calculate the initial velocity of the car. So we have given that there is a certain car which is moving with a certain velocity, and the momentum of this car is m times its velocity, whatever its initial velocity is. Then this car come and collide with this wall and then it comes to rest. That means its velocity is 0 now and its momentum would ultimately be 0. And this wall applies a force to stop this car in opposite direction, and this force is 27,000 newton, and this wall applies the force for 1.5 seconds, and we have to get this initial velocity. So to get the initial velocity, let us just see what is given. So we are provided with force and the time for which the force acts, and this is the definition of impulse. It is force and the time for which the force acts. There is also another formula which says impulse is equals to change in momentum. I'm using the first one. Impulse is equals to force multiplied by time. Force is for 27,000, time is 1.5, and this will give you 40,500 Newton seconds as an answer. The next thing that you know is that impulse is also equals to change in momentum. And we can split change in momentum as final momentum minus initial momentum. Let me write momentum in terms of its formula, which is m times v. So m times final velocity subtracted by m times initial velocity that we need to find. Substituting all the values that we know, impulse is 40,500, final momentum is 0. For initial momentum, the mass of the car is 950 and initial velocity is the needed value. Arranging it with respect to initial velocity, it would be 40,500 subtracted by 950. I am just ignoring the sign, and this will give you the answer of 43 meter per second. Second part is saying on figure 1.2, sketch a speed time graph to show the motion of a car for time t equals to 0 until the car becomes stationary. So there is a certain car which is moving with certain velocity, and then after some time, after 4 seconds, this car will stop. That means its velocity would be 0, and the car has deaccelerated through all the process, and we have to draw the graph of it. So let us just consider that the car started at certain velocity, let us say this velocity. So after it, the velocity is decreasing until the time has been 4 seconds. So the graph will look like this. Question number 2 says, describe an experiment to determine the spring constant of a spring. State the apparatus that you needed. details of how to take measurements, and how to calculate the spring constant. You may use the space below to draw a labeled diagram as your part of your answer. So, we have to determine spring constant. For this, we need to know what is Hooke's law. Hooke says that force is directly proportional to extension produced. That means if we have certain elastic thing, let us spring, and we just apply some force in it, or this spring will extend to certain limit, and this extension would be directly related to force that we have applied. Direct relation can be removed by a constant, so I have used K. K is the property of a spring, or we can say the stiffness of the spring. If we need to find K, we are going to divide force by extension, and some people call extension as X also. So, for the experiment, firstly we need a hook and then we need a spring, and we need to measure the length of the spring, which is unstretched length. That means that there is no weight on the spring, so the length is unstretched. Then we have to hang some kind of load on it. After hanging the load, the spring will stretch, and we have to measure the final length of the spring as well with meter ruler. And to know the extension that is produced, we'll subtract final length with initial length. So the apparatus that we needed was a hook and a spring, and we also needed some kind of load. We needed meter ruler to measure the extension produced, and we also need a spring balance to measure that the weight we are hanging with the spring. So what are the steps? Take a spring and measure its original or unstretched length and call it x1. Then attach it to hook and suspend a known weight to it and measure the extension that is produced. And after it, use Hooke's law, load over extension, and you will get your spring constant. B part is saying figure 2.1 shows a baby in a baby bouncer. The baby bouncer consists of a holder suspended from a spring. The baby pushes his feet on the ground and bounces gently up and down. So this kid is playing. There is a spring on which it is hanged, and he presses his feet, and the baby feels some jumps up and down. Total length is 140 centimeter, and this baby holder is 100 centimeter. That means we have only 40 centimeter gap over here. Two springs Q and R are tested to determine the spring constant. Each spring is tested up to its limit of proportionality. Define limit of proportionality. Hooke said that load is directly proportional to extension produced. That means the graph would be a straight line. But there comes a point onto this graph that after which the linearity relation doesn't hold and the graph start curving up. And this point is said to be limit of proportionality. Now what does it mean? What is the limit of proportionality? It is the point after which the direct relation of load and extension no longer holds, or you can say the spring has got damaged, the elastic behavior of spring has been damaged, or whatever is the reason, there is no direct relation that is fulfilling. So it is a point after which force is not directly proportional to the extension. Table 2.1 shows the results of the test. So spring Q has a spring constant of 7.8 and R has the spring constant of 1.1. The total weight of the baby and the holder is 120 Newton. So load is 120 Newton. Calculate the extension of each spring for this weight. So we have to calculate extension. We already know the formula that F is equals to K times extension. So if you want to calculate extension, it would be F over spring constant. So force is already 120 Newton and spring constant is also given, which is 7.8. So we'll just divide them both. So it would be 120 over 7.8, which will give you the answer of 15.3. When you round it off to two significant figures, it would be 15 only. But you know, this is given in centimeters because spring constant is Newton per centimeter. If you want to write it as it is, you can, but if you want to convert into meters, it would be 0.15 meters. Doing the same for the next 120 over 1.1, it would be 109.09. Rounding it off to two significant figures, it would be 110 or 1.1 meters. Second question is saying the unstretched length of each spring is 25 centimeters. State and explain which spring would be more suitable for the baby bouncer, spring P or spring Q, and you have to give your explanation as well. So if we see, the spring Q has extension of 15 centimeter and R has extension of 110 centimeter. And the unstretched length of spring is 25 centimeter. So we have only area of 15 centimeter that is suitable, because if this length extend, the baby's feet and the whole leg would touch the ground. So the Q spring is more suitable because it has only the extension of 15. So it has a right amount of extension for 120 newtons of weight. Okay, the next question is saying figure 3.1 shows a portable shower used on a campsite. The bag is filled with water and the water is heated by using IR radiations of sun. So this is a shower and this is the setup. Explain why the shower bag is painted black. So there are infrared radiations that are falling on this bag and this bag is being heated up. Why is this painted black? Because black is very good absorber of heat, and as well it's very bad emitter of radiation, so it will also prevent the heat loss. So black color will absorb more radiations and will get heat up quickly, and also it will prevent the heat loss as it's a bad emitter. Second part says explain a disadvantage of radiations from the sun being the only source of heat for this water. So why it's not useful? Because it will not work at night, because at night we don't have sun. B part says solar energy is a renewable energy resource. State two other renewable energy resources. I am naming wind energy and tidal energy as two new renewable resources. You can name any. C part says during the day the sun shines on the shower bag and some of the energy in the infrared radiations from the sun transfer to the thermal energy stored in water. The water absorbs 60% of the energy incident on the bag, and the temperature of the water rises from 10 degrees Celsius to 43 degrees Celsius. The mass of water in the bag is 40 kilogram. The specific heat of water is 4200 joules per kilogram degrees Celsius. Calculate the energy incident on the shower bag during the day. So we are supposed to calculate the energy that was given as an input to the shower. Let's suppose we have a shower bag on which there are UV radiations falling as an input, and this bag is using 60% of radiations to give some kind of output to us. And what we are supposed to find is the total input of this bag. That means incident energy. For this, we can use the efficiency formula, which is energy output divided by energy input times 100%. And the efficiency is 60%, so I can write 60 over here and writing all the values as they are. Energy output over energy input times 100. We need to get the input energy, the energy incident on the shower bag, but I can also find output energy because the information is provided, change in temperature is given, mass is given, specific heat of the water is also given. So the energy that is being consumed as an output can be calculated by this formula, specific heat energy formula. Mass is 40 kilogram, specific heat is 4200, and change in temperature is 33 degrees Celsius. After calculating all these, your output energy would be 5.5 into 10 raised to power 6 joules. That means this is our output energy. I'll just arrange this equation with respect to input energy. So it would be energy output over 60 times 100. You know the output energy is, we have calculated it just now. It's 5.5 into 10 raised to power 6 divided by 60 times 100. So the final answer is 9.2 into 10 raised to power 6 joules. Question number 4 is saying figure 4.1 shows a ray of light as it enters a side of a plastic block. The ray of light passes from air into the plastic. So this is incident angle, this is refracted angle. Show how the speed, wavelength and frequency of wave in the plastic ball as compared with their values in the air. Speed of light is greater in air as compared to solids and liquid. So that means speed of light when it enters plastic will reduce or decrease. And refraction is the process in which frequency is not disturbed. Frequency before refraction and after refraction is same. So I am writing frequency will remain same. Now what about the wavelength? You know the wave equation. As long as frequency is constant, so there is a direct relation between velocity and wavelength. So if velocity is reduced, for sure wavelength would also be decreased or reduced. Next question is saying show that the refractive index of plastic is 1.4. For this we will use Snell's law. According to Snell's law, N1 sine incident angle is equals to N2 sine refracted angle. What is N1? It is refractive index of first medium. This is incident angle. N2 is refractive index of second medium and it is refracted angle. You know incident angle is 45 degree and N1, the refractive index of first medium is 1. And refractive index of second medium is that we need to prove it, and the refracted angle is 30. So I'll put 1 over here. Incident angle is 45 and 2 is the value we are supposed to find, and R is the refracted angle, which is 30. I'm arranging this equation with respect to N2. It would be sine 45 over sine 30. And putting all this into your calculator will give you 1.4 as the refractive index of glass. Second question is saying calculate the critical angle of the plastic. The formula which is appropriate is refractive index equals to 1 over sine of critical angle. I will arrange this equation with respect to critical angle. So critical angle will go that side and refractive angle will come this side. And I'll take sine to that side as well. It would be sine inverse 1 over n. Putting the value of n, which is 1.4, and this will give you answer of 46 degrees. B part says figure 4.2 shows same plastic as in part A used to make an optical fiber. A ray of light is passing along the fiber. Carefully continue the ray of light P until it reaches the other end of the fiber. So this is a ray of light which is entering into the fiber and it will undergo total internal reflection, in which angle of incidence is equals to angle of reflection. I will continue the ray until it reaches the corner of optical fiber. I'll draw a plane over here. After drawing the plane, I'll draw a normal which is 90 degree to the plane. After drawing the normal, which is like this, I will measure the angle of incident ray, which is this ray making with my normal, and this ray is making approximately 64 degrees with my normal. So I'll make a reflected ray at 64 degree as well. After making a reflected ray, I'll see it is again falling on another corner of optical fiber, on which it will again undergo total internal reflection. So I'll make a plane again. I'll make a normal again on the plane, which would be 90 degree to my plane. After making the normal, again I will measure the angle of incidence of the ray with my normal, and I will again draw a reflected ray at the same angle it was making on the other side. So this ray will approximately fall this side. As you can see, it is falling on another part of an optical fiber. From this part, it can just go outside the optical fiber. So you have drawn a complete path of optical fiber and it will get you 2 marks. Next question is saying state 2 uses of optical fiber. So I am naming telecommunication and endoscopy as well. Question number 5 is saying figure 5.1 shows a metal sphere S. The sphere has been charged with a negative charge. There is an electric field around the sphere S. On figure 5.1, draw 4 field lines to show the pattern of field and indicate the direction of field with arrows on the lines. So for positive charge and negative charge, the electric field patterns are different. For positive, it's outward, and for negative, it is inward. As the sphere is negative charged, so the electric field line would be radially towards the charge. Figure 5.2 shows a position X next to a sphere S. A small negatively charged particle is placed at position X. State that direction of force on negatively charged particle X due to electric field around the sphere. So this sphere has a electric field around it due to which it will exert a force on negative charge plate placed at X. Both are negative, so they will repel each other. If they were opposite, they would attract each other. So this X charge would feel a repulsion towards this left side. So I am writing the repulsion force would occur towards left side of the page. The negatively charged particle X is released from rest. Describe the motion of the small negatively charged particle due to electric field around the sphere S. As you know that the force is acting towards left side, so it will obviously accelerate towards left side of the page. So I'm writing accelerate away from the sphere towards the left side. That's it. B part is saying figure 5.3 shows sphere S being sprayed painted. The sphere S is negatively charged. As the paint particle exit the wide nozzle of the paint spray, they become charged with positive charge. So this is a spray which is used to paint the sphere. Explain why the paint particles spread out when they leave the nozzle. The answer is that since they are like charges, so like charges repel each other and this repulsion will cause their spreading. So when the particle leave the nozzle, they get positively charged. All of the particles will be positive. That means they are like charges, so they will repel each other and this repulsion will cause their spreading. Next question is saying that the sphere can be painted by hand using a paintbrush. Suggest and explain one advantage of using this charged paint spray for painting the sphere. So why haven't we used a paintbrush and instead we are using this gun? Because it has positively charged particles, sphere has negatively charged particles, they will attract each other and their finishing would be very good, the paint would be very durable. So I'm only writing one reason. This will make the paint more durable because unlike charges will attract each other and this will make the paint long lasting. Thanks for watching the video. If it was helpful, please hit the like button and subscribe my channel.